Okay, let's look at a few examples. I don't know why I do that at the start of every video. Let's look at a few examples of the band structures in some metals. In fact, some nonmetals. So let's start with, as an example, why don't we take a look at potassium, okay? So potassium has atomic number of 19, so the electron configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, fantastic. So that's that looks really good. Let's see if we can draw out the band structure for this. And we got the electron energy here on the vertical axis versus what don't we do versus interatomic spacing. That'll work well. Interatomic spacing. Again, as we did in the previous video, we'll go from infinity here, and we'll bring it into R equal to R naught, the equilibrium interatomic spacing. So, and we're looking at, what are we concerned with? We're concerned with the valence electrons. Okay, so the what we're going to have here is we're going to have 4s, and there's only one electron in it, and that'll become important in just a moment. And so as we approach R equal to R naught, get these levels spreading out like that. But remember, there's, if I draw the box diagram, how many electrons can you fit in that? You can fit spin up and you can fit spin down. So similarly, there's two available states for electrons, but we've only populated half of it, right? We've only got, over here, we've only got one electron in it. So if we, and as we often do here, we'll say, well, let's just take it at absolute zero, where there's no thermal excitation, and let's shade in the occupied states, because there's half the electrons are there, and if we put them all in the lowest energy, that's where they're going to be. So this is then the filled states, and that's the valence band. Okay, remember, we get the band structure just by going and saying, okay, at R equals R naught in the solid, we draw a little two-dimensional sketch of that. So it would just look like this. And we've got these occupied states, the valence band. Over here it would be this. Okay, and then we've got unoccupied states. These are states that we can promote an electron up to. If we've got a bunch of atoms in the solid here, and they've each got their little electrons, we want to get conduction. What we want to do is we want to free an electron up and allow it to conduct through. Okay, so we want to put enough of an energy in to free it up, and to do that, we promote it up into the conduction band. That's the conduction band, and that's what we have over here. So in metals like potassium, there is, as you can see, no band gap. No band gap. Okay, fantastic. Let's take a look at another example. Let's take a look at a metal like, we're doing well, right? This seems to be working. We can explain conductivity. We can even explain, metals being shiny. There's, photons can excite an electron up, and then it drops back down and re-emits. So magnesium has atomic number of 12. All right. So we've got 1s2, 2s2, 2p6, 3s2. That's 12 electrons. And we'll draw the, actually, if you don't mind, well, you know what I'm going to do? Yeah, I'm going to draw, as I did before, be systematic about this. We'll have the spacing here versus the electron energy. Okay, that's the electron energy. And then we're going to go all the way to R equals R naught. And we're going to have our, this time it's the 3s. Okay, but this time we've got 2 electrons in it. And similarly, it's going to spread out like this. And this time, though, even at absolute zero, all those states are occupied. Uh-oh. You're saying, what's Ramsey up to? What's going on? I thought he said that we need to be able to promote with no band gap, but there's no available states here. If I draw my band structure. Right, we go from here to here. That's your band. What does that look like? Draw the band structure. It seems at this point like we've got our full, this is full of electrons, right? This is a full valence band. So where are we going to promote electrons to? There's nothing up here. But here's the answer. Okay, that was a weird face. Here's the answer. It turns out there's actually this 3p state available. Now there's no electrons in it in the ground when it's at absolute zero, no thermal excitation or anything, is empty. But as it approaches equilibrium interatomic spacing, what happens is it crosses over and overlaps with the valence band. Overlaps with the valence band. So now what do we have? Well, now we've got this conduction band that's empty. And again, it's immediately adjacent to the valence band, which is full. But because and it's adjacent like that, there's no band gap. We can promote up directly, easily. Just that, a photon, visible spectrum can come in and excite across that band gap, no problem. You put a voltage across a metal, and it'll conduct electricity because you will get enough. You'll be able to promote electrons up to conduct electricity, even just with that voltage applied. Now, what if you have something else like? Well, let's take a look at another example of silicon. Okay. Well, now silicon, you might remember, is sp3 hybridized, and if we go all the way to its band structure, it's going to look like this. All right, where we've got this occupied valence band, and then we've got the conduction band, these available states. But you'll notice we pass through this band gap in the middle. Okay, and the analogy here is in an isolated atom, it's like going from, say, n equals 1 to n equals 2. You can't go to n equals 1.5. We cannot have an electron promoted here. So we have a semiconductor. Another example would be carbon as diamond, and it's going to look actually kind of the same, very similar to silicon, okay, except the band gap is bigger. So we get the valence band, the conduction band, and this is, think of this band gap as how much energy you'd have to put in to ionize an electron away from its nucleus. But in this case, the band gap is a little bit bigger. And how big is the band gap? Well, the band gap for diamond is actually 5.5 electron volts, versus for silicon, the band gap is equal to 1.1 electron volts. So now we compare this to the visible spectrum, these photons of visible light. Well, what do you think the color of silicon is going to be? We get 2 to 3 electron volts, visible spectrum coming in, hitting silicon. It should cause promotion of electrons across that band gap, and then a moment later they drop back down and re-emit. Silicon should be shiny. In fact, give me a second, I can get some silicon. Alright, so there's some silicon. Sure enough, it's shiny. Why? Photons are hitting this, promoting electrons, dropping back down, re-emitting. This happens to be a single crystal of silicon. It's gorgeous. We'll talk about that in a bit more detail later. What about diamond? I got some diamond too. Alright, so this is my silly joke, right? It is diamond. I mean, this is the structure of diamond. I unfortunately don't have a piece of diamond with me that I could just show you. But diamond, you might know if you actually saw a real piece of diamond, is optically transparent. Why is that? Because the band gap is 5.5 electron volts. Photon of visible light comes in, 3 electron volts, violet light, the most energetic photon, boom, it goes straight through. It cannot excite across the band gap, so diamond is optically transparent. Okay, so those are a few examples. I hope that's useful. Thanks a lot.